Hi, Dora. Thank you. The stage is yours. Go ahead. Yeah, that's the one.
Thank you for the introduction. Hello, everybody. Very happy to be here. My second time in this amazing city. My name is Dora, and I'm a core data scientist at a company called METRO.digital. I'm Italian, but I live in Düsseldorf in Germany. Like you can see from the slide up at my back, here is going to be about learnings and data science. But actually, I want to share with you, for about 7 years of my life, I've actually been working as waitress. Raise your hand if anybody of you in this room did the same job before? Waiters, waitresses, even now maybe? Okay, so you may know, like me, like I do, that it's a job that apparently is easy, but in fact requires a lot of memory. And there are a lot of concepts as well, like a glass goes well with some beer or other kind of stuff. And despite working there for 7 years, if you ask me now, I forgot most of those concepts. But there is one thing I will never forget. Writing 6 mozzarella sticks meant customer wants 6 pieces, and writing 6 times would mean a customer wants 6 portions. And the reason why I remember this fact is there was a day I made a huge mistake. And I wrote 6 portions instead of 6 pieces. So there was then a lot of fried food being cooked, which me and my colleague had to eat before the boss could figure out. And that was a lot of fried food, yes. And that's also why I remember this fact, and that's why I remember this concept. So most of my, the other things I forgot, but this one will always stay. And why does it stay? Well, because it was a mistake. We are here now in this room, coming from different industries, all of us data professional probably, all of us made mistakes during our careers. I made many, and I'm here to share all of them with you. I value and treasure those mistakes, because without them, I would probably not be the person I am today, and I also think we need them to be better at our jobs. So I want you now for a moment to think back at your professions, think about the moment of realizations where you really thought, I messed up, I did hear something very bad. It feels very bad in the beginning, but then we need to treasure those moments. The mozzarella sticks moment of our careers are there to teach us a lesson. So here is what's gonna happen. I am going to go through 3 use cases powered by machine learning, where I had the pleasure to work on during my 5 years with this company. We're gonna go through what I did wrong, especially, and what was the lesson learned out of those use cases. So let's talk about the bad. Let's talk about the mozzarella sticks moment of my career as a data scientist so far. But before we can delve into the details, I need to tell you a few words about the company. We're talking about Metro. Pretty sure many of you know this company. It is active in 628 stores all over the world. It's a B2B, so the customers of Metro are themselves businesses. Think about hotels, think about restaurants, traders, kiosks, from the small ones to the big ones. And because customers are themselves businesses, the company has a strong focus on professional food and non-food articles. From a fast query, I could find about 90,000 products as sold only in Germany, only in 1 year, and there is 18 more countries to consider. So that makes a lot of data, especially considering all of the customer product interactions. Customers account about 2 million distinct ones in Germany in 1 year. And data is a great source of value for data science. They come from, obviously, the website. It's in the form of user clicks, session data, scrolling, clicking on a search query, typing queries, whatever, you name it. Also from the Metro app, following same concept, we also have data coming from devices that are employee-facing. That means we have employees doing their activities in several stores all over the world, and they interact with a device. They need to resolve situations, they need to make sure everything is up and running, and now this is as well data we can use for machine learning. How do we use it? To support them doing their job. So by enhancing, by the means of machine learning, the activities they are performing. Last but not least, every customer at Metro needs a Metro card to enter the store because it's a business to business. This is as well a great source of data. We not only know all transactions that happen in any store in a given point in time in any country, we also know who was the person performing this transaction. So think about, is it a restaurant? Is it small, big, where it's located, and so on. I want to make a side comment. We respect data privacy, and we don't make use of any sensitive information. We don't make use even on session data and so on if the user didn't consent to cookies. And METRO.digital is the company where Metro becomes digital. Here is where we have a lot of product teams sitting in different places. They take care of different functional areas. Data science belongs there. And it's not a department itself. It's rather data scientists, data analysts, even data engineers and machine learning engineers sitting across different product teams. So they are not all together in a department. They are sitting within the product. We have this organizational structure because we believe it's the best way to really understand what the problem is when we want to do data science. So like I promised, we're going to go through 3 use cases powered by machine learning and my mistakes during this time. Recommendation system is my main area of expertise because it's where I was allocated from day one. This team takes care of building recommendation systems from scratch using the Metro data. And these recommendation systems are displayed across several channels. Frequently bought together is one example. This is something we are familiar with. We want to find real-time products that go well together and display them for the customers to see them on the app, on the website. Alternative recommender. This one is there because of the out-of-stock problem. How many times did you want to buy something that was not in stock? It's really annoying. Like we are used to very fast interactions with the devices nowadays, and if something is out of stock, why not replacing it with something similar? That's alternative recommender. The third one, last but not least, is called rank promotions. Here we get promotional data from marketing. They decided to do a marketing campaign with barbecue, and now we want to rank these articles, make them personalized for the user who real-time is logged in a certain device. So very challenging. The team is heterogeneous, made of a product owner, data scientist. It was mainly me, then we became 2. The software developers, a data engineer, and a data analyst. I had a great time working in this team. We built a lot of versions of the 3 recommendation systems. What typically happens is we have the data scientists looking at the business case, talking to the stakeholders, figuring out the problem. Then we are going on notebook. We are building a lot of different possibilities for a recommendation system. And then it comes this crucial moment in time that I'm pretty sure many of you in this room can relate to. We have done benchmarking of several, say, algorithms. Sometimes they are just simple business rules. They don't have to be fancy at any cost. We have a baseline model that's there for saying, here is the minimum acceptable level of quality we want to achieve. We have a test data set of unseen data, and now everybody is waiting for this moment. On average, it took us 6 months to get here. We have this table, and we need to say, we are ready for production, yes or no? Are we confident that quality is good? And so we see here, these are real data from one of the recommendation systems we have live at the moment. We see the following. The model here is better than the baseline on several metrics, typical for recommendation systems. And the quality is also sufficient on the long tail. We are interested in this long tail because most of the articles are not so popular. We have a giant cat, tall 1 meter in concrete that nobody is interacting with. And still we want to have sufficient, say, replacement or recommendations also for those hard cases. That's why we score the long tail separately. And now here, fine. I was a junior data scientist in the beginning. I was just out of university. You go with this confidence. I know the theory. I did my work, and I know what I have to do. But then we have to go live. So when we move live, the world is different. We left the lab, we finished our experiments, and now it's time for A/B testing. Here is about making sure whatever we built in a lab is working in real world. In the recommendation system team, we used to split group A, group B are 50% of user sessions. They are subject to different versions at the same time. And what we're interested in is the statistical significance that user clicks, so now we're speaking about business-related metrics, are increased with respect to the new version rather than the old one. We have been doing this A/B test for a year across several different countries, several different recommenders, even several different versions, sometimes tiny changes. We had so many of them. This was a great point of observations for me. And what I realized, what was my main mistake, if I now look back at that time? Very often I've seen assumptions from our offline experiments, so that table I was showing before, are not reflected in the A/B test. There were times where we were very confident, we built a great recommender system, and then pushing it live in production, it will not result in a great A/B test. And there was also the opposite. Sometimes we were just making a tiny change and just to test something, push it to the A/B test and see the opposite situation. Like, it was very promising. It was increasing even revenue by far. So I was asking myself, what is the main reason? And this one moment where I started to question, it's the mozzarella stick moment of the first use case. So it's a moment where I realized I messed up. What is my mistake? So I did a little bit more in-depth research around what are good metrics for recommender systems. I entered the area of MLOps a little bit more because it's also about monitoring quality after production is there. And I can tell you, sometimes, it's not always the main reason, but sometimes we overestimate the quality of our machine learning solutions. And one reason why we may do this is we have a bad choice of a baseline model. Baseline models are, by definition, simple. They are also standard. For the recommendation system area, a baseline model, you can think about a random recommender. Random recommender is mentioned in many papers in the recommendation system. You take at random some items. You can do this with the query. It doesn't have to be fancy. And now you score this one simple logic against the recommender system itself. And I was doing this blindly until I realized, is it really making sense to have a random recommender to benchmark something else? Isn't it too simple? The probability of getting at random a good recommender system in the particular moment when the user is viewing something is 1 divided by 90K in the Germany dataset. And that's very low, and it's too easy to beat, let's say. So I started to wonder, is there anything better we can do with baselines when it comes to recommender system? And here is my learning coming from this thinking. Pick your baseline like a kid would do. And this is the best we can do. In the context of the A/B test we would try to perform, the natural baseline for this one case is not the random recommender. It's probably the old version that we are trying to beat. That should be scored offline before we go live against the new version. The second possibility is, OK, we really want to do random, then we can do it, but at least within the subcategory. I can tell you this one recommender system is already pretty good. If you are viewing candies, it will recommend you other candies. It's not that bad, but if we don't do better than that, it's a big problem. The further advantage we have picking the right baseline is a good baseline can be pushed to production. So whenever the model is being scored against the baseline, whenever it's not better, why not go with a simple model, with a simple baseline? So here is my learning. Pick your baseline like a kid would do. The second mistake I had made in my initial time as junior data scientist was not paying attention to metrics. We leave university, we do courses in data science, we learn a lot of concepts, we learn to pick the right metric. And you have seen them, NDCG, hit ratio, precision, these are all specific to the task at hand, they are not wrong. But there is an issue. We hope to see business metrics reflected when we push to production. They are different, and we have no guarantees whatever we optimize offline is going to be reflected into that one metric we want, revenue, clicks, purchase-through rate. So I was researching around this issue, and I found a very interesting paper, which is linked with my presentation at the end. Is called the ML test score. Here is a paper from the Google research about MLOps. they suggest to pick baselines that correlate. We want the online metrics to correlate with the offline metrics. And this is, I find, a very interesting hint, because it's relatively simple to monitor metrics when we are already live. Why not starting to look at the bigger picture, take a step back, look at the product itself, not only staying focused within the niche area, like just the coding and the machine learning. This was very helpful for me. I found very interesting findings, which led me to the next point, the next mistake that I had done. This one, mozzarella stick moment, came from observing. Okay, is this even enough? I tell you no, there is more to it. The most impactful experiment we performed in 1 year across all countries was not related to improving the model. It was related to improving the technical metrics. This was a moment for me of realization. I stepped back and I tried to think. We made the recommendation faster, and this was the highest impact we got in 1 year A/B testing online. What did I do wrong in this case before realizing this simple logic is technical metrics also have an impact on the A/B test. We were monitoring all of them, but we were monitoring them in a separate dashboard. This one was not really a mistake, right? But having them together, shown together in the same place, monitored together, helped find out that that was the case, or probably the cause. I say probably because causality is something different, for our experiment to perform good. So here is my learning. Always monitor technical metrics and machine learning related metrics together. So I had a great time working in this team, doing recommendation systems. It was 3.5 years. It came then for me the time to move to a new team. This is a team in METRO.digital that specialized in product search. And they were, again, a heterogeneous team of software developers and the product manager. What they were doing is taking care of a scenario where all of us are familiar with. We are users, we all see a search query and where we can type free text. This team is responsible for ensuring the list of results that are displayed to a user query are relevant. But there was a problem. There was complaints coming here and there from the countries, from the stakeholders. You know, search was not always good. How do we define a good search? I can give you a real example that was presented to me when I joined this project. Typing salt may result into bathroom salt, as maybe first article returned. And now is it bad to say that bathroom salt is not salt? No, it's not. But it's not what the user wants. Most of us, when we type salt, we want to see plain cooking salt. Why was this happening is the tool that was in place for doing the search was not paying attention to semantics. It was doing token matching. It was looking into the query, salt, and searching within the assortment for products that would contain the word salt. And it's not bad. Like, most of the time it works fine, but there are these now edge cases where it's particularly bad. And now in the search context, when we see one example, we make a judgment on the whole system that, oh, search is really bad now. So the question was, is there anything machine learning we can do to help search become a little bit smarter and understand the meaning of a user query? Yes, there is. There is methods to help search improve by using semantics, and this is looking into the area of NLP, natural language processing. We had a very tight deadline of 6 months, and it was only me and another software developer working on this problem, so we searched for a solution that could be rolled out fast. We collected the past history of all of the user queries that were on the French website in 1 year, the list of all the articles that were displayed in correspondence, and the user clicks. And now the logic was pretty simple. If most of the clicks are on article at position 5, we want this article to be position 1. So that's what the model is learning by means of this ground truth, which is user clicks. Click-through rate is the most correct term. So we worked for 6 months, no stop on the problem. I was making sure I don't do the same mistakes again. So metrics, so thinking about the A/B test, thinking about stuff that I had learned in the other team. But yeah, then we got to this point. We sat together with the business stakeholders to identify, to make a quality judgment. We extract at random a query, we type something, and we ask the model to give us back a search. And here is one example where it's really, the use of NLP, of semantics, is really helping. Typing Christmas decoration would result for the machine learning model to understand it's Christmas. The emphasis is on Christmas. The old system would put emphasis on decorations, and that's obviously not what the user wants to see. This is one striking case where our solution was better than the previous one. Another situation where we really could see it is for hyped queries. It was Corona time, and toilet was among the most popular queries at that time. Everybody was searching for toilet papers. And the old system would focus on signs that go on the bathroom door, and the machine learning model could understand it's toilet paper, and why is there? Because everybody was clicking on these items, and the driver for the model was clicks. Now I want to be honest with you, it was not always so clear. We saw a lot of situations where the two were comparable and very hard to say which one was better. I'm just showing to you the edge cases where that was really, really striking different. The business stakeholders liked it, we pushed it live, and we, guess what, A/B tested it. So 50% of the requests go into the machine learning model, and now surprisingly, the other 50% go into an external vendor, not the old system. The decision was taken to test our solution against an external vendor which is specialized in doing search. Here I started to be a little bit nervous because that was unexpected. We were measuring user clicks, and by bigger surprise, we found out we were beating the external vendor. So the new version of search was even better than solutions we could buy outside. So now we could think, what did I do wrong in this one situation? Well, I tell you, despite performing better, we did not go for this solution. We went for the external vendor. This was another mozzarella stick moment, the mistake I've done in this use case. I started to reflect, what did I do wrong this time? And I can tell you, looking at this picture, this is taken from a paper from the Google research again. This is code that's being built for machine learning in a machine learning project. It's this dot in the middle, and the rest comes around. So there is so much more, apart from the machine learning model, that we have to think about when we want to build a product that is using machine learning. We had to be putting all of the efforts into there without thinking of the big picture. And that's something we do because that's what we learn. When we learn to be data scientists, we learn that the model is everything, and the score of the model is everything. I can also tell you, I would add, oh, that's the paper. I would also add to this, two main blocks are important: communicating with stakeholders and competing with external vendors. That's what happened to me. I did not really pay attention to the full picture. I did not pay attention to the importance of being a salesman, a saleswoman. The importance of being there to defend your solution, to show that you know how to put it into production, that there is a plan, that there is people there to support, and we know how to proceed from here. Sometimes the data scientist has to wear the hat of a salesperson and be the first supporter of his or her solutions. And if this is not happening, that's what we risk. I also want to add, the external vendor came with a plug-and-play solution. In our case, it would have needed longer to go really like up and running and maintaining and everything. The team didn't have the resources for it. The last use case I want to talk about is something I'm still involved in. But I am there as a sort of internal consultant. There is other data scientists working on this one use case. I'm supporting them. It's super interesting. The problem setup is facing an employee device and not a customer device. We're talking about in-store operations. We have big stores, really huge. They have 2 floors, a huge amount of products in assortment, and the employees have to do a lot of tasks. Think about finding expiring items. This is already very hard without the support of a device. And we have a great team in a METRO.digital column store, which is based here in Romania, and it takes care of an app that looks like this. It supports employees do their operations. The point in the middle, markdown, is where the machine learning is happening. The employee we'll see a list of products that are about to expire in a few days. And now an action needs to be taken. They can be thrown away, they can be donated, or a discount can be applied. If we don't apply the right discount, we may risk losing revenue on these products. So there is a value trying to identify the correct discount to apply to products. But the employees don't have the time and they don't have the data view to make this decision. So up to this being done with machine learning, it used to be business-driven. And now the team decided to display the discount automatically by means of a machine learning model, displayed in the employee app, such that they could know directly what is the optimal discount that maximizes the sold quantity, minimize food waste, and yeah, creates then additional revenue for the company, obviously. The team had already built a machine learning model which was live in 3 countries, and there was an A/B test running in 1 country for over a year. The A/B test was putting in comparison the business rules done by a human and the model. The machine learning model doing automatically certain discount. And now we are measuring revenue, and we are asking ourselves, is the machine learning model better than the humans or not? And we also want to improve on next versions around this problem. So it's a super interesting use case. The people working did a great job. I think I was there to... My goal there was to try and identify improvement opportunities on top of this one use case. We worked very much on the machine learning, and we tried to benchmark different algorithms, different parameters, improve here and there, do more hyperparameter tuning, like the classical data science stuff. But the moment of realization for me with this one use case was, I actually noticed that data-related improvements here created the highest impact. Every time we tried to take a step back, look at the data and think, why data is missing, for example? How could we do better imputation upon missing data? Talking to the stakeholders, talking to people who is expert into this scenario, incorporating that domain knowledge into the data analytics up front, even before the data science, this kind of thinking led to the best improvements. And we all learn the following. When we are doing a data science project, we need to do an exploratory data analysis in the beginning. This step is fundamental and it's important. And again, it's what we learn in courses, what we learn in university, what we learn anywhere when we want to start our career in data science. So we look into outliers, we look into missing value, we look into the classical way of doing data cleaning. And this was in place, and it was, I would say, also correctly done. But I also want to add, the machine learning solution is much more than a notebook, and it's much more than one stand-alone data analytics. There is a machine learning pipeline. This we have in all solutions live. The machine learning pipeline takes data automatically, does the cleaning automatically, then it's maybe joining table, maybe then training the model, scoring the model, and pushing the results. And this is done automatically. The pipelines refresh themselves. We have 1 per country, and this is how we go to production. That's pretty standard. However, I was thinking, at a certain point, came in my head, these components here, they are nothing else than Python code under the hood. Sometimes TensorFlow, but Python. And that exploratory data analysis we do one time, and we do as a separate block. Why not moving those analyses inside of the machine learning pipeline? This one change was revealing, not only in this one use case, in many other where I was involved. Refreshing those analytics is so much impactful on monitoring the model, the quality, dealing with bias, and it can be so simple to implement. We just need to do a copy-paste of code that we already have. Whenever the model is refreshing the data now, also the analytics behind data is also refreshed. And by a click of a button, we can see here is on GCP, the tool is called Vertex AI. We implement those components custom for us. There is an HTML file, sort of a report of data. How is data looking for Spain versus Croatia versus another country? Doing this kind of cross-country comparison, in addition to looking at the analytics of the data set, helped us figure out a lot of tricky situations, and this was the most impactful in this one project. So I tell you, do your exploration in automation if you can, if you have a machine learning pipeline at hand. Just move the code there. That's it. And now I've been saying a lot of negative things about working in data science. I've been mentioning all of my mistakes, what I did wrong, that I will try not to do again. But sometimes when it works, data science can be really cool, and it can be really, really impressive. So I have prepared for you a video upon visualization. This one came from one recommender system I was building in the recommender system team. We had built this recommender in the context of collaborative filtering to understand what similar people may like to view or to buy. So the concept is, if two people are displaying a similar behavior, and one is interacting with pizza and fries, they are a good candidate for being recommended to the second person, which is very similar. This one recommender system, okay, it was live and up and running, but it comes with the side results that I decided to upload in a tool, which is open source by TensorFlow Research, called Embedding Projector. It looks like this. It's open source. It's on the web. One can type Embedding Projector and see it. Now what you see here is the tool, but the data that it's inside coming from our own recommender system. Every dot that you see in this visualization is a product in the Germany dataset, and 100,000 points is 100,000 articles. And I decided to color differently, red and blue for food and non-food. And now I stop for a moment. Oops, you can see already, they are separated already. Why is that? Because the algorithm can figure out food and non-food are different at the eyes of consumers, and therefore they belong together, but not so together. And in this map, we can as well zoom in and out. Try to get it to start. By scrolling with the mouse, we see what the product is. Products have names. I just concatenated the names to what the product that is. You see, okay, 100,000 points. And now here the concept is, the closer these points, the closer we calculated those items to be based on user behavior. At the right side, there is a search bar where I am typing pasta because it's something I understand as Italian. And now, by doing the search, you will see the tool can do a search on the names. And that's nothing to do with our results. But what comes from the recommender system is actually a quantitative measure of distances between any product to any other. So I pick one, and this is 500-gram orecchiette. It's a type of pasta, and I'm looking into the neighbors of this product. And like you can see, almost everything is pasta. But there is a substructure into this. I could find, for example, that this side on the top is spaghetti in the same brand, in the same quantity. And they are said to be very similar to each other. And we don't know by how much. To the bottom, you see a cluster of pasta, subcluster, that is having filling. For example, triangoli, ravioli, and so on. They are not own brands, so not the brands of Metro, and they have a similar quantity. So one can explore a lot of these properties. Like, we spend a lot of time looking into what makes products similar to each other. And now here is the power of machine learning. You don't get this from a database search. Like, I could search for pasta in a database, and I will not find the following. I will not find these nuances in product similarities. Next is I search for candy, and here is now Haribo. It's a brand, and it's the most wanted, the most distinct people search for Haribo in Germany, so that's why. And this one product also has neighbors, and you see two clusters, one on the top, one at the bottom, and this is more far away. In this one scenario, what makes them separated is the pack size. At the bottom is Haribo that is sold in a carton package, and on the top it's all in a bottle, so it's sort of individual pieces into a box. So once again, one could spend half a day looking at these properties for any given, even looking at the macro structure. It's beer products next to auto. Yeah, I'm going a bit stereotype. Okay, so what makes it also powerful is the same map we have for customers. Now, I'm not presenting this to you because we don't do anything with it, but we can also say for any customer now how closer they are to each other based on what they buy. And when we see 0.9, I can tell you we read the shopping and they're really buying similar things. So it was really impressive. It's something that it's a side result of one machine learning project we have. I found it very, very interesting. So here is a summary of my mistakes that I've done in my 5 years as a data scientist. And here is the learnings I gather through this time. So pick your baseline easy, take a look at metrics, at the whole picture, not only the data science metrics, also the product metrics as a whole. Monitor the technical metrics together with the data science metrics. There are times where you need to sell your algorithms to other people. You either have to compete against other companies internally. And last one, don't forget exploration and automation. So look at analytics and automate your analytics if you can. I want to conclude with a quote about making mistakes from Henry Ford. He says, "The only real mistake is the one from which we learn nothing." So there is no bad mistake. We need these mistakes. We need it to be better at our jobs. Do more mistakes, the good ones. And when it happens, it feels bad, but then take a step back and think, what do I do better the next time? I want to add to this wise quote, do it whether it's about mozzarella sticks or data science. Yeah. So thank you. This is my LinkedIn profile. If you want to connect, if you want to talk about any of the mentioned topics, I will be here around. We have a booth downstairs. We also hiring data engineer. So if you are a great data engineer and you want to join, talk to my colleagues. Thank you.
Thank you. Thank you. It's a good thing your presentation was after lunch because this was a 3-course presentation. We had like mozzarella sticks for antipasti, then the different types of pasta, and ended with haribo. It was perfect. I'm sure everyone would have been hungry. Thank you for your presentation. I'm sure that those of you working in e-commerce or retail have found it very insightful. Actually, if you have some questions, we have time for 1 or 2. If not, as Dora was saying, you could find the METRO.digital booth. Let's see some hands. Do we have some hands? No hands. One hand there. Can we get the mic there, please? No questions about proprietary technology this time,
Of
please.
course.
Thank you.
So I think this was one of the most technically substantial and articulate presentation. Thank you for this.
Thank you.
I think it's a good standard for the other presenters. Now, you mentioned that you're using MLflow for MLOps, but you said this just before you were showing some Vertex AI pipelines. I guess you're using Vertex AI pipelines for serving the models. How you connect? I guess you register the models still with MLflow. How you connect the information with the Vertex pipelines?
Okay, very good question, thanks. The machine learning pipelines are implemented on Vertex AI, which is a product on Google Cloud Platform, like I mentioned, allows for building components and automate the whole process of gathering data, doing all the steps, machine learning, scoring, and then they are taking over from the engineers. There is an API typically at the end. The MLflow is having a lot of functionality when it comes to machine learning, and this is open source. The Google Cloud Platform is not. We use only the part of MLflow that is doing the metadata tracking. So we use it for metadata tracking. In theory, the Vertex AI has itself a section for doing metadata, but it was still initial stage when I was working on that project. And it didn't allow for comparing experiments. So when we have a lot of experiments done across different pipelines, we want to be able to compare metrics, compare what was the data set size, what was the country, and all of that. So that's why we use MLflow to compensate for a lack of similar in Vertex AI. And it's integrated. We built a component called MLflow tracker, where we call the MLflow, and in every component we log what we want to see to be able to monitor the model quality. So we typically log the shape, we log everything we think is interesting, and even artifacts can be logged, and even plots can be logged. Then when there is multiple runs, and we want to compare quality, we select them together, and the ML flow is doing telling us what the metric was, even the hyperparameters that generated the model are there. And this is helpful, especially when we are assessing quality in the beginning. Later on, when the model is there and running, we don't look at it anymore unless we see bad metrics. So if there is, in a dashboard, we see, oh, now the metric is going down, and we need to look into it again. We, again, rely on ML flow to tell us what metadata generated what model that led to what results. Yeah. Thank you.
Thank you.
Thank you. Thank you for your answer. Thank you for your question. Unfortunately, we're out of time, but you can find Dora at the METRO.digital booth. Round of applause, Dora Petrella.
Thank you.
METRO.digital.
Thank you.
Thank you.